So we're going to finish up with this perfect hashing method, okay? So yeah, so the great thing about perfect hashing is that you can actually create a hash table with no collisions at all, okay? So that's kind of a remarkable thing. And also this hash table is not very large, okay? So if you're trying to store n items, right, you don't want to use like a super large hash table, right? If you have a very large hash table, it's easy to make sure that there are no collisions, okay? But the great thing about this perfect hashing method that we're talking about is that this can actually use linear space. So if you're trying to store n items, you're only going to use something like 2 times n amount of space, or maybe 3 times n, okay? So it's linear, and also the constant factor in that big O, it's not too large, okay? So this is actually a pretty practical way of doing hashing with no collisions, okay? And of course, the great thing about not having collisions is that now you're guaranteed to get constant time performance, okay? Whereas in like with universal hashing, you're gonna get expected constant performance, okay? With perfect hashing, you're guaranteed to get constant performance, okay? Yeah. So does anyone have any questions about how the perfect hashing is working? Any questions? So it's like a 2-layer hash table, right? Oh, something wrong with this printout over here. Well, what is happening? So, where did these come from? Is somebody drawing on my screen? Wait, I'm doing screen sharing, and then I am, wait, did I allow other people to draw on the screen? Because I don't want to allow that. All right, so I don't know what happened there. But anyways, yeah, so this is not coming out very well. All right, so there's this 2-layer hashing scheme, right? So oops, let's switch to add nodes. All right, so the first, so there are 2 steps, right? The first step is you hash to somewhere in this first level hash table, right? And oh, let's change to a different spot. Okay, so let's say that you hash over here, right? And then, so this is using the main hash function, this h of k function, right? And then after that, now that you know you're going to the location number 2 over here, right? Then you're going to use this function h2 of k, right? So in fact, this function is stored in the hash table itself, because all these hash functions, they are defined as okay. So guys, give me 1 second here. All right, I'm gonna fix up the formatting problem. Okay, so not sure what that problem is, but just give me 1 second. Okay, so the let's see. Yeah, so the hash function so this is supposed to be what? 3k plus 42 here. Okay, and this is modulo mod. This is mod 101. And then this whole thing is going to be modulo the table size, which is 9, right? Because you have this, this table is going from 0 to 8, so that's 9 entries, right? And then here, this thing over here is going to be, each of these is going to be this aj times k plus bj, right? This is, again, modulo 101, right? And then this whole thing is going to be modulo this m sub j here. Okay, so that given that, so suppose you know that you hash to the second entry over here. Okay, then you see that these values here, a2, right? Because we're talking about 2 over here, so we're talking about a2, b2, and m2. Okay, they're stored in this table entry right here. Right, and then you can use this to create your new hash function for this index 2 over here, which is h of 2, right? And now you're going to have to apply that hash function to your key, and then that's going to take you to somewhere in this hash table. Okay, so you just do two hashes, and then you do 2 hashes and then 1 memory access. Okay, or sorry, not 1 memory access, but you're going to do 2 memory accesses. Okay, right? You're first of all going to read these values over here, right? And then second of all, you're going to apply that hash function and then go to one of these memory locations. Okay, so 2 hashes and then 2 memory accesses, and that is all you need to do, and and then you can check for your key. So any questions about this? All right, now I want to mention that so the great thing about perfect hashing is that there are no collisions, right? So there's actually another hashing method that we can use, which also doesn't have any collisions, okay? And this is called cuckoo hashing. Okay, so I just want to show you guys how cuckoo hashing is going to work. Okay, we're not going to talk in too much detail about this because there's actually fair amount of research on cuckoo hashing and different variations of cuckoo hashing. So it's a pretty interesting topic. But today I just want to show you how basically how it's working. Okay, so 1 second here. I think I need to make this smaller to make my pen look a bit larger. Okay, so this is cuckoo. These pictures are illustrating cuckoo hashing. Okay, so we have two scenarios over. Let me switch to red. So we have two scenarios over here: the A scenario and B scenario. Okay, so I'm going to go through the A scenario first. Okay, so basically in cuckoo hashing, well, there are different ways to present this. Okay, so for simplicity, I'm going to say that for cuckoo hashing, we're going to have two different hash tables. The T1 here and the T2 here, okay? And then for each hash table, you're going to have a different hash function, all right? So there's like a hash 1 function over here and a hash 2 function over here, all right? And now for every key that you're trying to insert, you can apply either H1 or H2, okay? If you apply H1, that's going to give you an index in table 1. Right? If you apply H2, it's going to give you an index in table 2, right? And then for cuckoo hashing, you're always going to start by applying the first hash function, H1. So you're trying to find a location in the first hash table, which is free. Okay? So for example, let's say that, so here, let's do another example. Okay? So suppose you have a value, U over here, okay? And suppose that when you apply H1 to U, right, let's say that you get this location, okay? So this location currently is unoccupied. Okay, yeah, so cuckoo hashing, right? But by the way, so I'm gonna digress a little bit. So cuckoo is actually a bird, right? And so the special thing about this bird is it's actually kind of a nasty bird, because what it does is it's gonna, so the mother cuckoo birds, okay, they're gonna lay their eggs in some other bird's nest. Okay, so they're not gonna build their own nest, they're gonna lay their eggs in some other bird's nest, plus they're gonna kick out the eggs which are currently in that nest. Okay, so it's sort of like I go over to your house and then I kick you out and then I live there, okay, or my children live there. Okay, so that's what this cuckoo bird does. Okay, and the reason they call this cuckoo hashing is because this is kind of like how this algorithm is also working. Okay, you have this thing where you kick out other values. Okay, so I'm going to show you how this kicking out other values part works. Okay, all right, so then getting back to this example, we have this value U over here, which is being hashed to, let's say, this empty location. Okay, so because it's empty, then now you can just go ahead and store U over here. Okay, so that's the best case scenario, where you apply H1 and then you find an empty spot and then you simply store the key and the value there. All right, now, but the other scenario is that now suppose here you're trying to insert this value X over here. Okay, so now these two arrows indicate that if you apply H1, then X is going to go over to this location, okay, on the left. And if you apply H2, then X is going to go to that the location on the right, right? And then, but because we're always going to apply H1 first, okay, so then we're going to try to put X in the first hash table, the T1, right? But the problem there is that you see that this Y here is already occupying this location. So in this case, for cuckoo hashing, we're actually going to kick out Y, okay? And we're going to put X where Y used to be, right? So this is this thing about the bird I was saying, right? So this cuckoo bird, this X, right, has found this location where Y is currently sitting, and then now X is going to sit there, and then he's also going to kick out Y, okay? All right, but of course, you can't just kick out Y and then remove it from the hash table, right? You have to still store Y somewhere in the hash table, okay? And that's what these arrows indicate, okay? So you notice that there's always an arrow from from like one table to the other table, okay, either T1 to T2 or sometimes from T2 to T1. And what this is indicating is that, remember, each value has two possible locations, one in the first table and one in the second table. Okay, so for example, before we inserted this y over here, right? The fact that there's an arrow over here indicates that if you applied the h1 function, you would put y exactly over here. But if you applied the h2 function, you would put y over here. Okay, so you simply make an edge between the two possible locations for each value. Okay, so each value has two possible locations, and you just put an edge between them. Okay, so that's what all of these edges indicate. All right, so now getting back to this, so we were inserting x, right? So x is going to get inserted into here initially, right? This is going to kick out y, okay? Or we also say evict y, okay? So we're going to evict y, and now y, the other possible location for y, we can find that by just following this arrow, okay? So then that means that y is going to get evicted and then put in its other location, okay? All right, so now y is going to sit in this location, but previously z was over here, right? And now that you're putting y here, you're going to have to evict z, okay? You're going to kick out z, okay? So then z is going to follow its arrow, right? And then that's indicating that z, so the location for z in table T2 is this location, okay? But the location for z in table T1 is going to be this location, okay? So now we can just put z in this location, and because this location is now unoccupied, right? Because before we put z there was nothing else there, okay? Then we're now done, because once you put z in this open spot, you don't need to evict anybody, right? There was nobody there, so there's nobody to evict, and so now we're done, okay? All right, so just to summarize, the procedure for using cuckoo hashing is that you have these two tables with these two hash functions, okay? Whenever you try to insert a key, you're first of all going to try to insert it into the first table, right? If it's open, then you're done. Okay, if there's no entry there, you're done. If there is another key there, then you're going to put your key, like the X key, in that location, but you're going to evict the current key. Okay, and the current key is going to go to the other table, right? Either it's going to go from T1 to T2, or it could go from T2 to T1. Okay, but it's going to go to the other table, and if the other location in the other table is open, then again, we're done. But if that location is also occupied, then we're going to evict whatever is currently in that location. Okay, so then that new guy is also going to try to go to the other table. Okay, so you could have this chain of evictions, right? Like X was evicting Y, right? Y evicted Z, right? And then Z could have evicted somebody else, and you could have had this big long chain. Okay, but eventually, if you ever get to a location in one of these tables that's open, then you're done. Then you can finish. Okay. All right, so then we can look at the performance of this algorithm. Okay, so so let's first of all look at the time to do a search. Okay, to do a lookup for a key, and the great thing is that the lookup operation is always going to take constant time. In fact, at most you need to do 2 hashes. Okay, because at most, like for example, this value X here. Okay, it can only be one of 2 possible locations. Right? Either it's in this location here in T1, right? Or it could have been in this location here in T2. Okay, but those are the only 2 possible locations for X. And so that means that if you want to search for X, then you just you apply H1, and if you don't see X there, then you apply H2. And if you still don't see X, then that means that X is not in the table. Okay? So it's constant time for lookups. Okay. Now for the insertions, it's actually more complicated. Okay, because for the insertions, what we saw was that you could have these evictions. Okay, so you could have like a chain of evictions. Okay, and in fact, this chain. So in the example on the left, right, for this A example, right. So we had a chain of like 2 evictions. Okay, but you could actually have much longer chains. And in fact, your chain could be can sometimes not terminate. Okay, so you can have like an infinite chain. Okay, you can have a loop. So let me give you an example where you actually have a loop of evictions. Okay, yeah, and by the way, if you ever have a loop of evictions, then that means that this insertion is going to fail, and then you're going to have to rebuild the hash table. Okay, so I'll tell you a bit more about what happens when you get a loop later on. Okay, but let me just first show you how a loop can possibly occur. Okay, so let's see. Hopefully I can work through this example. Okay, so I think what's happening here is that we're trying to insert x. Okay, so we're going to put x over here, which is going to push y over here, which is going to push z over here, right? Which is going to push what was over here? Oh, this is u. Okay, right? So and then that's going to push u over here. Okay, but u, you see, or sorry, u now is going to evict v, right? So then v is actually going to go over here. Okay, v is going to follow this edge and go over here, and that is going to evict x. Okay, right? And then x, right? So x, the two possible locations for x were either this location in T1, right? This location in T1, or this location in T2. Okay, so now because v evicted x, we're now going to have to put x over here, right? But then that is going to evict t, okay, who is going to go over here, right? We're going to follow this edge. And then that is going to evict s, okay? So then s is going to go over here, right? And now we have a loop, okay? We have a loop in the evictions because x has been evicted both from its location in table T1 and its location in T2, okay? And so that means that x has nowhere to go, okay? Because, for example, if you put x back over here, okay? If you put x where v is, okay? Well, that's just going to cause this entire chain of evictions to happen again, okay? So you can't put x in T1, and you cannot put x in T2, okay? Because if you put them in either if you put x in either T1 or T2, it's just going to cause these this chain of evictions to go on forever. Okay, so this means that it is not possible to insert x using this these two hash functions. Okay, so then what you're going to do in that case is that you're just going to restart everything. Okay, you're going to just rebuild your entire hash table. Okay, so your entire hash table has the entries are, you have x, y, u, v, z, s, t, right? So you have like 7 entries over here. And we're just going to completely build a new hash table. And when you do this, of course, you're going to use new hash functions. Okay, because if you use the same hash functions, you're going to get the same problem. Okay, so imagine that you have like a universal hash family. Okay, and then we're picking these h1 and h2 out of that family. Okay, so for the current h1 and h2 that we selected, we happen to get unlucky, and we ended up with this this cycle over here. Okay, this eviction cycle, and this means that it's impossible to build this cuckoo hash table using these two functions h1 and h2. So therefore, we're going to pick new hash functions, like let's call them h1 prime and h2 prime, right? And then we're going to try again, right? So now that you have, guys, can you hear me? Can you guys hear me? Okay, all right. Okay, so this Zoom is not very stable, but Tencent is also not very stable. All right, well, 我的两不好，我的网不好。Okay, I see. Okay, all right. Sorry, getting back to this. Okay, so what happened is if you pick new hash functions, right, then all of these different values are going to go to completely different locations. I mean, probably, right? Because you have a new hash function, so s might go over here, right, and then u might go over here, and so on. Okay, right, and then hopefully with these new hash functions, the cycle of evictions is not going to happen again. Okay, so that is the hope. right? So in fact, you can show with good probability, as long as your table is not too filled up. Okay, so if you fill up like 99% of T1 and 99% of T2, then it's very likely that you're going to get these eviction cycles. Okay, but you can show that if T1 and T2 are both about half empty right now, then with high probability, you're not going to get a very long eviction chain. Okay, and then and also with very high probability, you're not going to have an eviction cycle. Okay, so if you have a short eviction chain, then that just means that you have to evict a bunch of guys before you can eventually find a location. Okay, before you can eventually finish your insert operation. Okay, but if you have an eviction cycle, then that means that you'll never finish your insert operation. Okay, so you can prove. So I'm not going to do this, but it's possible to prove that if these two tables are sufficiently empty. Okay, so for example, they're half empty, then you're both going to have a short eviction chain, so that your insertion operations are pretty fast, right? So it's basically going to be logarithmic time, okay, logarithmic in the number of entries. Okay, so you're going to have fast insertions, and you're not going to have these eviction cycles, so you can always insert new items. Okay, so yeah, so that's cuckoo hashing. And again, the benefit is that you have constant time lookups, because you at most you need to do 2 hashes. Any questions about that? Okay. Yeah. So if there are no questions, then today, today we are going to talk about these Bloom filters. Okay, so this is another randomized data structure. It's actually very popular. Okay, it's used all over the place. Okay, and the Bloom filter. So I mentioned this in the I hope you guys looked at, let's say, the first I don't know, like 10 or 20 minutes of this video lecture. Okay, so so hopefully you guys at least know what the Bloom filter does, right? And the nice thing about the Bloom filter is that it's very memory efficient. Okay, so it does something. It does close to what the hash table does. Okay, meaning that you can use it to keep track of a set of items. Okay. However, there are 2 weaknesses. Well, there's a couple of weaknesses to Bloom filters. One is that you can only store keys in the Bloom filters, or in fact, you can only check whether keys are present in the Bloom filter. You cannot store values associated with the keys. Okay, so in a hash table, you can store the keys, and then each key can be associated with a value, right? Like you can put a big string associated with each key. Okay, when Bloom filters, you can't do that. Okay, you can only keep track of which keys are in the Bloom filter. Okay, and okay, so another problem with the Bloom filters is that you can only add new keys to the Bloom filter. Okay, you can't delete keys. Okay, so it doesn't support the delete operation. Okay, and then finally, the problem with the Bloom filter is that it's not completely accurate. Okay, because sometimes, so if you ask the Bloom filter whether an item X is in the set, okay, so sometimes it can give false positives. So meaning the Bloom filter says, yes, X is in the set. Okay, however, X is actually not in the set. Okay, so that's a false positive. Right? But the nice thing is it will not give false negatives. So if the Bloom filter says X is not in the set, right, then you're sure that X is not in the set. Okay. So yeah, so that's what the Bloom filter does, and then this actually has like a surprisingly high number of applications, right? So just the simple semantics of being able to keep track of a set of keys very memory efficiently, and then even though you're getting false positives, right? You could get false positives. You have a low probability. Okay, so just this functionality, you can use it in a bunch of applications, especially when you need to access like some sort of storage medium, which is slow. Okay, so like this example with the database, right? So if you need to access a database, that's slow. Okay, so you don't want to So you want to avoid accessing the database as much as possible. So basically, you're going to summarize the database using a Bloom filter. Okay, and then you can access the Bloom filter, and that's going to be very fast because the Bloom filter is very small. So so maybe it'll fit in your cache, or I mean, it'll definitely fit in your memory. Okay, so your database is probably sitting out on disk somewhere, right? So that's going to be very slow to access, but you can definitely keep the Bloom filter in memory because you're using something like 10 bits per entry. Okay, regardless of how big the keys are, you're only going to use 10 bits for each key. Okay, so you can keep like millions and billions of keys in memory. Okay, so that avoids you having to go out to this database, right? And then also on the web, these are Bloom filters are used for many sort of web caching type applications, because again, to try to access some data on the internet, that's even slower, right? That's going to take you like several seconds as opposed to several milliseconds, right? Your disk you can access in several milliseconds, but if you go online, you're going to need to spend like hundreds of milliseconds or maybe several seconds to access something. Okay, so you definitely want to avoid having to unnecessarily go onto the internet. So then instead you keep this Bloom filter in memory, and you can access that in like a microsecond. Okay, so that's like 1,000,000 times faster. Okay, right. So did you guys look at how the Bloom filter works? So, well, I guess I'll start today's lecture over here, okay, with this slide, just in case there's some people that have not looked at how the Bloom filter works. Okay, so yeah, so I'll do that in a few minutes. All right. Are there any questions about anything I talked about so far? Here's a question. After getting that the expectation of the numbers is how to get the actual number. Right. Okay. So the yeah. So if so we're gonna get to this later, but Tianyi is asking about this this high probability bound over here. Okay, so this can be done using something called Chernoff bounds. Okay, so in fact, next week we're going to talk about these Chernoff bounds, which so the Chernoff bounds let you not only compute the expected value of a random variable, but it'll also say that the random variable is going to be very close to its expected value with very high probability. Okay, so here the expected value is something like 1 minus p times m. Okay, and then the Chernoff bound is going to allow you to say something like it's going to be with very, very high probability. Okay, with like 99.9999% probability, it's going to be either at the expected value or something like plus minus something like square root m. Okay, so here so the expected value is something linear in m, right? It's 1 minus p times m. Okay, and then you're within like sort of a with high probability, you're going to be within like a standard deviation of that, or a few standard deviations of that. Okay, so the standard deviation would be something like root m. Okay, so we're going to see that next time. Okay. Any other questions? All right. So then why don't we take a short break until like 1:35? Okay, so let's just take a break for 4 minutes, and then we'll come back and then do the rest of this.